Hello, everybody. My name is Markus Wagner, and I'll be presenting joint work with Jakob Bossek on generating instances with performance differences for more than just two algorithms. Diversity nowadays is very important in many domains. For example, when you're planning the mine, how it should be excavated, which blocks to go in which sequence. Of course, you optimize with respect to known objectives, but you also might have to show to the actual mine manager different alternative plans, in particular with respect to larger mining sequences. In another domain, in inspirational image generation, it might be very important to generate images that are very similar in quality and overall structural similarity to a particular seed image, but then other aspects like skin color, eye color, hair color, they should all vary and be as unbiased as possible. For us as algorithm engineers, it's very important to understand algorithms, to tune algorithms, to create well-performing algorithm portfolios. And here, generating a set of instances on which some algorithms perform as differently as possible can be very beneficial to driving this research in the first place. I'll briefly present some background. About 10 years ago, we started with performance diversity of instances on the traveling salesperson problem. And so we wanted to construct a set of TSP instances on which the performance of one algorithm varies. And the fitness function that we used to drive this process was the simple approximation ratio. This is defined as follows. We take the performance of a particular algorithm on an instance I and divide it by an optimal solver divided by that is run on the instance I as well. Back then for TSP, we used, for example, Concord as our reference. This resulted for various solvers, for example, or 2opt in this case, in easy and hard instances that we as humans could easily differentiate. We could make up some structures here. Given that this already uses two different algorithms here to compute the approximation ratio, we can ever so slightly generalize this to actually creating diverse sets of instances where two solvers are performing as differently as possible. All you have to do is take one performance divided by the other performance, and then you're trying to maximize essentially the distance between the performance distance between these two. So this all happens in the performance space. In the feature space, things are ever so slightly different. And in particular, I want to briefly show that going from sometimes just 2 points in space to 3 or more can at times be challenging unless you have a clever idea. Let's assume we have a particular instance I that has a particular feature value. And these feature values might be from some range from some minimum value to some maximum value. So this instance I sits here at some spot in the range. We might have another instance I-1 sitting a bit further to the left, and instance I+1 sitting a bit further to the right. Now we can define the diversity of a single solution here, instance I as being the area, whatever, essentially the cuboid, with respect to the neighbors that this instance occupies. So in this case here, instance I would sit in a rectangle that is made up by the distances to the neighbors. We can generalize this easily to an entire population where all the different, so assume you have more instances to left and right, where we end up taking just a sum, potentially weighted sum, over all these rectangles. And with this now, we can calculate, for example, for another instance, where the neighbors are a lot closer, also the diversity, and then we might decide, hey, this particular instance I down here contributes very little to the overall diversity of the population, so we might actually omit this or drop this in the next iteration. For the next iteration. This is now the single feature space. We can, of course, combine this. And this is what we've done a few years ago as well. So we evolved in the first step instances only using the easy instances using the approximation ratio. And as a side effect, we observed that the mean distance to the centroid of these instances, TSP instances, were in a particular range here. We evolved hard instances, again, using only the approximation ratio, and we observed that mean distance to the centroid was in a slightly different area. And now we might draw the conclusion that this particular feature is important for an instance, or it helps us characterize it, and we might even end up training an algorithm selector on this data, which intuitively is a clever idea. But we have found out that once we evolve easy instances while focusing on feature diversity, so combining both, we observed that, hey, we can actually observe mean distances to the centroid in a very wide range. And more importantly, it very much overlapped with the one of hard instances. So this invalidated our original observation quite badly. This is just to show you very briefly that you have to be careful when you're drawing conclusions based on feature diversity or the lack of feature diversity. So I'm slowly getting the transition to today's topic. Diversity optimization is still a hot field. About 2 years ago, we had a breakthrough where we managed to formulate the problem of feature diversity optimization with respect to 2 or more features. This was relatively important because we had to be as unbiased, or we had to be unbiased in the higher dimensional space. Higher dimensional optimization, you might think of evolutionary multi-objective optimization. Slight trouble there is that you would end up preferring a particular range over other ranges, and we explicitly did not want to go there. There's a lot more work out there, including theoretical analysis. If you want to learn more about this, feel free to have a look at this tutorial here. The open question of today in this very present paper is the following. How do we evolve instances on which 3 or more algorithms perform as differently as possible? For example, we might think of an instance I1 where algorithm 1 performs better than algorithm 2 performs better than algorithm 3. And for another algorithm, other instance, we might prefer algorithm 3 to be performing better than algorithm 1, better than algorithm, algorithm 2, and so on. And we might have lots of these targeted permutations. We've used 3 different approaches for this, and well, in all of them we used a very simple 1+1 evolutionary algorithm where the initial instance was generated at random, and then we ended up mutating the instance, and we accepted it if it was no worse with respect to our fitness function than the previous instance. But the smarts are really, this is where the smarts are in the fitness function. What shall our fitness function actually be to drive this? The first idea was very simple. We used the pairwise approach. So considering all n times n-1 ordered pairs of algorithms, so assuming we have capital N algorithms, such as 3 in the previous example, but it could be, of course, any larger number as well. We evolve for every single pair in isolation in individual runs an instance. This is obviously very easy to formulate with existing technology, but a single run then ignores all the other algorithms. And as a side effect, we might accidentally end up having an instance that is easy or hard for all other n-2 algorithms. So it's not optimal there, not fantastic. Second approach termed no order. Our approach is there the following. We sort the performances of the different, in this case, 3 algorithms on the instance. So this is performance of algorithm 1, performance of algorithm 2, performance of algorithm 3. We calculate the distances. Again, we use the crowding distance like what we would have done previously with just a single feature. And we can maximize this. We can do this obviously for 3 algorithms, and we can extend this easily to multiple algorithms as well. The advantage is that this uses fairly established technology again. So this is 3 out of 4. But we just need to get lucky to hit a desired permutation. The trouble here with the desired permutation is what we are addressing in the third approach, the explicit ranking. In particular, we use a 3-tuple to implement 2 phases. The first one is we try to match the desired ranking, and then the second one is, as before, we try to maximize the performance difference between the different performances. To get there, we need, again, the following. We need the performances, much like on the previous slide, P1 to Pn of the various algorithms, and we need pi as the desired ranking. Now, once we have with respect to this desired ranking, pi, we calculate the number of good directions and bad directions, so good pairs and bad pairs. So some gets a thumbs up, some get a thumbs down with respect to our target permutation. And once we've counted these directions, we do the following. We maximize lexicographically the 3-tuple that first consists of the number of good directions, and then the We have as components the distances, there's some technical details omitted here, the distances between the bad pairs and distances between the good pairs. This might look unnecessarily complex, but it was actually necessary to achieve local sensitivity. In our case study, we used a combinatorial optimization problem called the traveling thief problem. I will omit more details here. The only thing that's important for now is there's one component that consists of a permutation and another component that consists of a bit string. We had three algorithms, three heuristics, that randomized heuristics that we used here. One targeted only the bit string, one targeted only the permutation, and one targeted both alternatingly. The remaining setup is not too much interest now. Let's see, how often were we actually successful in our experiments? It turns out quite successful when the potentially superior algorithm C2 was the one that should be performing best. So we had success rates of 80 to 90% here for just pairs. The other way around, we were not as successful. I should have mentioned that we imposed a particular time limit, so it is not too surprising. It was still a bit surprising to us, but it's not too surprising that sometimes the simple heuristic can actually outperform the more complex ones here. We see a very similar pattern for the explicit ranking for even triplets of algorithms here as well. Not super high success rates, and here we even did not get lucky at all, but nevertheless we were successful in some cases. A slightly different projection of this data is as follows. Effectively, we should have had 40 different or 40 instances for every single target combination here produced by every of the three approaches. But we did not get to the 40 everywhere. But having said this, nevertheless, we have about 30 to 40, 30 instances here, where 20 instances here where C2 performed worst, and another 20 instances here where again C2 performed worst. It was a pleasant surprise that we managed to achieve this nevertheless. Why was our success rate not 100%? Well, there was a whole lot of noise in the system, and sometimes even the algorithms behaved a bit bimodally, in the sense that either they were stuck in some bad local minima or good local optima. And depending on how often you sample them during evolution, we used the 5 samples and then took the median. We ended up either getting lucky or unlucky, and this irritated the evolutionary algorithm at times. So of course we can address this by running the algorithm for longer, but this also costs computation time than during the optimization itself. Secondly, because algorithm C2 was more powerful, it was more difficult to evolve instances where C2 was outperformed by the others. Let's have a very quick look at the instance space itself, at the feature space. We used principal component analysis to have a quick look at this 400 to 2400 dimensional space. And interestingly, when looking at the instances where C2 is the worst performing one, they are in a relatively distinct space from the others. Well, not so much the other one where C2 in this particular sequence, there are red dots all over the place, red circles, but these two here, the red crosses and the yellow diamonds here, they're in a relatively, well, sharply concentrated space. So we have to be careful, because here we optimized only for performance diversity, not for feature diversity. We have to be careful when drawing any conclusions here from this. Similarly, when looking at a particular instance, so this is one instance where C2 performed, one single hand-picked instance where C2 performed worse, very highly clustered nodes or items in an instance where C2 performed best, not so highly concentrated. But again, these are just 2 examples out of hundreds and hundreds of instances. Long story short, about 10 years ago, we were only able to evolve hard or easy instances for a single algorithm, and nowadays we can do this for multiple instances in high dimension spaces, possibly even subject to a minimum quality constraint. What remains now to be done is we want to study custom variation operators for diversity optimization. We want to see how can we change state-of-the-art solvers to compute diverse sets of solutions. This can not only be of interest to a decision maker, but also be beneficial during a run. And we would like to learn from you, how can diversity be helpful to you? If so, how and why? Thank you.